We're in 17.2. We're doing the equation of a parabola this time. The equation of a parabola is a little bit more complex than a circle, but it has some advantages, and we need to look at them. So the first thing we need to talk about is how we measure distances from a line. So how would I measure the distance, say, from this line to this point here? Well, we kind of covered this before. What we don't want to do is come in at an angle, right? That won't give us an accurate idea of the distance to something. So we would have to come in perfectly perpendicular. Keep that in mind when we're moving ahead here. In this instance, we can define a parabola as a set of points that is equidistant from both a point and a line. So our very first point that's equidistant, that's pretty obvious to tell, is going to be right in between, right? So if I was to just say, oh, this point here is equidistant from the point and equidistant from the line. There are other points too, though. You can imagine a point out here. Let's say you go out, this distance right about there. And similarly, there would be one right about there. You can do even more points, though. You can imagine a point equidistant like that and a point equidistant like that. And as it turns out, that's where we get our parabola shape from, is through that definition there. So we have a few terms here. Try not to get too bogged down in them. There's basically three that we really need. So we talked about a parabola, definition of parabola, and the point that is the parabola is equidistant from is called the focus. So that's the focus point. And then the line that the parabola is equidistant from is called the directrix. So here's the directrix, and here's the focus. And then finally, our third term is going to be the vertex. And the vertex is in this case, the bottommost point of the parabola. If the parabola was arcing the other way, it would be the topmost. It's where it's the point in between the focus, the part of the parabola in between the focus and the directrix, or closest to the focus and directrix, directly in between them. So that's one way to think of it. Okay, we're going to go ahead and derive the formula just like we did with the circle. So let's scroll down here. It says, let the focus of the parabola be, we're going to call it F, clever I know, but we're going to give it some coordinates here. We're going to put it at 0p. So in this case, we'll just have the 0x value. So we're right here on the y-axis. So the focus is on the y-axis, and its y value is going to be just little p there. The directrix is going to be at y equals negative p. And so the advantage of this, so here we are at y equals negative p, and then the focus is up here. The nice thing about this is that means that the vertex of the parabola is going to be at the origin. And it's a handy thing to have it in the origin. It allows us to have this simplified form when we do our first derivation here. So then they say, let point P be any point on the parabola with the coordinates x, y. Okay, that makes sense for all our lines. X and y are just any given point on that line. Let Q be the point of intersection of the perpendicular from P and the directrix. So let me erase this for a sec. So here's point Q. The coordinates for point Q, the x value is going to be the same as P, right? And since it's on this line of y equals negative P, it's going to have a y value of negative P. Sorry, I used P to talk about point P and then the value negative P. So don't get too confused by that. But that just means that our x value is x, and then our y value is negative P for point Q. Okay, so now we have two segments here. And remember, the definition of a parabola is that this point P is going to be equidistant from the point, and equidistant from the directrix. So that means that this segment is congruent to this segment, and we just need to define those segments. So the first part is to use the distance formula to find out what FP is, and then the second part is to use the distance formula to figure out what QP is. So F to P, the difference in X values is X, the difference in Y values is Y minus P, so therefore, suppose I move that. The formula is the square root of X squared plus Y minus P squared, right? From Q to P, it's actually a little simpler. The difference in X's is 0. There's absolutely no difference. So therefore, the length of QP is simply Y minus negative P, or Y plus P, right? We have an absolute value here because distance is always positive. Or you could think of it as we're squaring that sum and then square rooting it, which will always make it come out positive. Okay, so we both know both of those values are equal to each other. We can set those equal to each other, and now we just need to simplify. So the first step is to square both sides to get rid of the square root. So the square root disappears, and we're just left with what's inside. However, this is squared, so we need to square that stuff. Oops. So what is Y plus P squared? Well, we just cross multiply, right? You guys know how to do these polynomials. We get Y squared plus 2PY plus P squared. Over here on the left, the X squared is all by itself, he's happy. We have Y minus P, and we square that whole thing. Same sort of deal, Y squared, but this time minus 2PY plus P squared. Minus 2PY. So now we just have to start simplifying. We look for things that are the same on both. We got a Y squared here, we got a Y squared here, is that gone? We can subtract off P squared, and that just leaves us with X squared minus 2PY equals 2PY. Well, again, we're just trying to get the X's and Y's together in the same spot, get like terms together as much as we can. We have a 2PY here, we have a 2PY here. Note here, we can't subtract a 2PY because then it'll end up over there on the left. So we're going to add 2PY to both sides. 2PY plus 2PY is 4PY. And then the final step, it's almost optional really, is to solve for Y, just to get Y by itself, which means Y is equal to 1 over 4P times X squared. So, is this a function? Yes, because we can get Y by itself. Y equals. And that makes sense. If we go back to all our pictures, for every single X value, there's a unique Y value. Explain how the value of P determines whether the parabola opens up or down. Well, if P is positive, it goes up. If P is negative, it goes down. Explain why the origin 0, 0 is a point on the parabola with the focus 0P and the directrix Y equals negative P. Well, that vertex, right, that point on the parabola there, the vertex is going to be directly in between the focus and the directrix. And so the X value won't change, it'll be at 0. And then we simply need for a Y value the average, or the point between P and negative P. The value in between P and negative P, or the average of P and negative P, is 0. So therefore it's going to be at the origin 0, 0. All right, we'll do an example. Write the equation of the parabola with focus 0, negative 4, and the directrix Y equals 4. Okay, so what's our P value here? Again, the directrix is Y equals 4, so it's 4 away from the origin. The focus is also 4 units away from the origin. So note here, our value for P isn't, well, real quick, we'll just graph it real quick, I guess. Focus is at 0, -4, boop-a-doo-doop. Directrix is at y equals 4, boop-a-doo-doop. Which way is this going to open up? Well, it's actually going to open down. So we have a -4 as our value for p. To get the equation, we simply take our form equation, y equals 1 over 4p times x squared, and we plug in -4 for p, which makes 4 times -4, -16, so -1/16 times x squared. Furthermore, we can graph it. We can do that by plugging in some x values here. Oops. There we go. Sorry about that. The values they give us are -4, -2, 0, 2, and 4. Well, when we have -4 and then we square it, that gives us 16. What is -1/16 times 16? Well, it's -1. We can do the same thing for -2. -2 squared is 4. What is 1/16 times 4? That's 1/4, or -1/4. 0 is going to be 0, and then 2 is going to be the exact same thing as -2, right? This negative disappeared immediately. So we got the same values for -2 and -4 there. And this makes sense when we graph it. We can check ourselves. We can go to -4, -1, -2, -1/4, 0, 0, +2, +1/4, and 4, -1. Gives us this shallow little arc here. And we can see if we're close. Yeah, we're pretty close. So, yes. Okay, see if you can do this one. I'm going to pause for you. So pause. Okay, hopefully you got something similar with p equaling -1, because that's the value here, essentially. But again, we can double check, we can graph it. We see that the directrix, the average of the directrix and the y value of the focus is 0, so the focus is here at the origin. We can plug in x values, we can get y values, we get a nice pretty little graph with this nice little parabola facing down. Okay, one more thing we have to cover. Not all parabolas will have a focus at the, sorry, not a focus, I meant vertex. At the origin. Some will not. At which point we only have to make one little modification, and that is to put in our h and k. So where it used to say x, we're now going to say x minus h. Where it used to say y, we're now just going to say y minus k. Where h and k are the x and y coordinates for the vertex. You may recognize this equation here. In fact, I encourage you to just circle this one. The book doesn't do a good job of identifying this. So here's the equation for it. It's the same one as before, except here we haven't solved for y. It's just a little more intuitive if we keep y in the rest of the equation kind of like this, where there's no division and stuff like that. So it doesn't look quite as short, but it's actually computationally a little bit easier to work with. So here's our example. Our focus is at 3, 5. The directrix is at y equals -3. Again, since y is a horizontal line, in order to find the vertex, we simply need to find the average of these two y values. So this one has a y value of -3. This one has a y value of 5. So the focus is going to be at same x. So it's going to be at 3, and then what's the average of 5 and -3? Well, in this case, 1. So the focus will be at, sorry, the vertex is going to be at 3, 1. And that means that we know our values for h and k. H is equal to 3. K will be equal to 1. And we can simply use our form version of the equation and plug in 3 here and 1 here, which gives us something like this. Once we're done with all that, again, we can start plugging in x and y values and graphing it. Of note here, though, we can also just plug it into a version without h and k and then scoot it over appropriately. Because note here that this is the same as the equation for, say, the parabola, but the same parabola with p is 4. However, it's just scooted over 1, 2, 3, and then up 1. So the shape is the same, it's just been translated over. Okay, see if we can do this one. And I'll get it to you in a second. So pause. Okay, so for this guy, again, we'll pull this down too for you. Again, for this one, the focus is at 3, 2. The directrix is at y equals -4. So therefore, the vertex will be at 3. And then the average of 2 and -4 is -1. So this corresponds to our h and k values. H is 3, k is -1. When we plug a -1 in there to the equation, it ends up being y plus 1. Oh, and then our p-value. I never covered p, did I? We can calculate our p-value. P is simply the distance between the focus and the vertex here, right? Or the directrix and the vertex, either way. The difference between -4 and -1 is 3. The difference between 2 and -1 is 3 as well. So in this case, p is equal to 3. Just like before. What does the sign of p in the equation of the parabola tell you about the parabola? Well, if it's positive, it goes up, negative goes down. How is an equation for the general parabola related to the equation for a parabola with a vertex of 0, 0? Again, in this case, if the vertex is different than 0, 0, those just count for h and k, and then we substitute in x minus h and y minus k in the equation. Otherwise, it's the exact same. Okay, that's it. That's all I have. Good luck on the homework, and I'll see you guys next time. Thanks.